Imagine you're training a massive model, maybe a transformer or a high-resolution diffusion model with hundreds of millions or even billions of
Yeah.
parameters. Mathematically speaking, your training process should be fundamentally broken. I mean, because of the way mini-batching works, the stochastic noise that theoretically helps your model explore the lost landscape is just entirely
Yeah.
missing in like 99.9% of those parameter dimensions.
Exactly. It's wild to think about.
Yeah, your algorithm is essentially blind. It's completely deterministic in millions of directions, yet it still learns. It generalizes.
It does. And today we are looking at a paper that rigorously proves why you really only need noise in exactly one dimension to escape a trap in, a billion-dimensional space.
Right, which brings us to our mission for this deep dive. Since you listening are already deep into machine learning and data science on a daily basis, we are skipping the basics. We're getting right into the math.
So the paper is titled, Is Stochastic Gradient Descent Effective? A PDE Perspective on Machine Learning Processes by Barbieri, Bonforte, and Ibarrondo.
And what they've done is pretty radical, right?
Yeah, they basically abandoned the traditional view of SGD as just a discrete algorithmic loop. I mean, when you are operating in these massive over-parameterized regimes, tracking individual weight updates step by step just totally fails to capture the macro-level dynamics.
Right, the scale is just too huge.
Exactly. So instead, they model SGD as a continuous time stochastic process, specifically governed by parabolic partial differential equations of the Fokker-Planck type.
Which is fascinating. But before we can map how SGD behaves across different temporal regimes, we have to look at the massive mathematical roadblock the authors tackle right out of the gate.
Oh, yeah, the diffusion matrix.
Right, Q of X. This covariance matrix is generated by the noise of your mini-batch sampling. And in our standard setups, the parameter dimension, D, is vastly larger than the total dataset size, N.
And because the sum of the gradient differences across the entire dataset evaluates to 0, the rank of that covariance matrix is strictly bounded above by n-1.
Wait, let's break that down for a second. So if you have, say, 50 million parameters, but only 100,000 training examples.
Then the rank of Q is at most 99,999. The matrix is highly degenerate. It is completely singular. You have zero noise, like literal zero variance, in tens of millions of directions.
That is just terrifying from a theoretical standpoint.
It really is.
So to understand how that severe rank efficiency impacts training, we have to bridge the gap between the discrete code running on your GPU and the continuous PDE theory.
Right, and the authors utilize an Euler-Maruyama discretization for that. It demonstrates how discrete SGD updates actually converge toward a continuous stochastic differential equation.
And in that SDE, the parameter evolution is driven by basically two competing forces, right?
Exactly. You have the deterministic drift, which is, the negative gradient of your full loss function. And then you have the stochastic diffusion term, which represents that mini-batch noise.
And the scaling of that diffusion term is governed by what they call an effective learning rate.
Yes, denoted as epsilon squared. It's defined mathematically as the learning rate eta divided by twice the batch size b.
I have to say, I found that formulation just incredibly satisfying.
Oh, how so?
Well, because it provides this rigorous theoretical foundation for the empirical linear scaling rule.
Right.
I mean, when you were spinning up a massive training run on a cluster and you double the batch size to get better throughput, you just inherently know you have to double the learning rate.
Right, otherwise the training dynamics just collapse.
Exactly. And this continuous SDE naturally encodes that exact heuristic right into its core scaling parameter. It's not just a hack anymore.
No, it's baked right into the math. But the true analytical power here comes when we shift our perspective. Instead of tracking a single parameter state, we track the entire probability density function of the network weights over time.
Right. Rho of TNX.
Exactly. And this is where the Fokker-Planck equation steps in. It explicitly describes the evolution of that probability mass.
So it's balancing the divergence of the drift against the diffusion.
Precisely. The drift is constantly pulling the probability mass down the gradients of the loss landscape. Meanwhile, the second-order Hessian operator, acting on our highly degenerate diffusion matrix, is trying to spread that math out.
But because that effective learning rate, epsilon squared, is typically configured to be super small in practice, the early phase of training is almost entirely dominated by the deterministic drift.
Right. The noise is practically a non-factor at the very beginning. The authors classify this initial period as the drift regime.
And what happens in this regime? Because they prove something pretty wild in Theorem 1.2.
Yeah, they prove a massive local mass concentration effect. Wherever your initial parameter distribution happens to be, the probability mass is violently pulled into the basin of attraction of the nearest local minimum.
It's like a deterministic gravity well.
That's a great way to put it. And they establish a strict bound showing that the probability of the parameters staying confined within a rapidly shrinking ball around that initial minimum is overwhelmingly high up to a certain time threshold.
And the velocity of that mass concentration is exponential, right?
Yes, and it's strictly governed by the lambda convexity of the loss function within that specific basin. If the Hessian of your loss is lower bounded by a large lambda, meaning the basin is incredibly sharp, the mass collapses into the minimum almost instantly.
Okay, let's visualize the geometry of that degenerate space for a second. It's not just a simple ball rolling down a bumpy hill.
No, it's way more restricted.
Imagine you're navigating a massive million-dimensional maze. You have the freedom to walk in any direction in, say, 3 specific dimensions, but you are locked onto a rigid deterministic track in the other 999,997 dimensions.
Right, because of the degenerate noise matrix.
Exactly.
Yeah.
So during this drift regime, those deterministic tracks are angled steeply downward. You're basically on a freight train sliding into the nearest valley. And the tiny amount of thermal energy you have in those 3 free dimensions isn't nearly enough to derail the train.
You're just trapped in whatever suboptimal value you started near.
Right. So if the deterministic pull is that absolute, the big question is, how does the system ever explore? Empirically, we know SGD finds solutions that generalize. It doesn't just stay trapped forever.
Well, the small stochastic fluctuations from the mini-batching must eventually accumulate enough energy to push the system out, which brings us to what the paper calls the diffusion regime.
Okay, the diffusion regime. And they formalize this escape process by calculating the mean exit time, right? The MEP.
Yes, the expected time for the parameter state to breach the boundary of the local minimums basin. They frame this as an elliptic PDE boundary value problem.
And they establish precise upper and lower bounds in theorems 1.3 and 1.4. But looking at the upper bound, I have a serious mechanical question about the math here.
Sure, what is it?
We just established that the diffusion matrix is heavily rank deficient. There is zero noise in millions of directions. If the system is strictly deterministic across the vast majority of the state space, how can we mathematically guarantee a finite expected time to escape? It seems like it shouldn't be possible.
Oh, that apparent paradox leads to arguably one of the most elegant proofs in the entire paper. They demonstrate that you actually do not require uniform ellipticity to guarantee a finite escape time.
Wait, really? You don't need noise pushing in all directions?
Not at all. You only need strictly positive variance in a single dimension. Just one, provided that dimension aligns constructively with the geometry of the loss landscape.
Are you kidding?
Yeah.
So if the process is completely deterministic in a million directions, that single noisy direction has to, effectively drag the entire parameter state over the ridge of the loss basin.
That's exactly what happens. Mathematically, there just has to exist some vector v such that the quadratic form v transpose q of x times v is strictly bounded below by some positive constant beta.
How does the topology of the drift even allow that to happen?
It works because of how they adapt Cramer's law. In classical statistical mechanics, Cramer's law estimates the transition time of a Brownian particle escaping a potential well based on the height of the saddle point and the eigenvalues of the Hessian.
Right, but that's for normal non-degenerate systems.
Exactly. But the authors reconstruct this for highly degenerate matrices. As long as your one noisy vector has a non-zero projection onto the path leading through the lowest saddle point out of the basin, you're good.
Oh, wow. So as long as the loss function's growth is suitably bounded along that specific directional slice, the continuous stochastic process will eventually diffuse over the boundary.
Yes. The millions of deterministic dimensions simply follow the gradient flow. They don't actively prevent the escape, as long as the loss topology doesn't create an infinitely steep wall in the specific direction of the noise.
That is just incredible. Okay, so the drift pulls the mass in, and the highly restricted diffusion eventually pushes it out through the saddle points.
Yeah.
The parameters successfully jump between minima.
Right.
But if we let this continuous process run indefinitely, what happens as time approaches infinity? Does the probability mass actually settle into a stationary measure, or does it just perpetually cascade through the loss landscape.
Proving asymptotic convergence for a strictly degenerate Fokker-Planck equation is notoriously hostile mathematical territory.
I can imagine.
Yeah, the standard techniques for proving the existence of a steady state heavily rely on the diffusion matrix being uniformly elliptic, meaning you have non-zero noise across the entire state space.
But because our Q of x is singular, those standard functional inequalities just completely break down.
Exactly. So the author's initial strategy to bypass this involves a theoretical construct called noisy SGD. They modify the discrete update equation by injecting an artificial isotropic Gaussian noise term into every step.
Like a tiny delta of noise across all dimensions.
Right. Delta times the identity matrix. It forces the overall matrix to become uniformly elliptic.
Okay, I have to push back on that, though.
Yeah.
Introducing isotropic Gaussian noise fundamentally alters the algorithm.
Wow.
Practitioners training large models are not injecting artificial noise into their gradients just to satisfy uniform ellipticity requirements.
Really true.
They're running standard degenerate SGD. Isn't this noisy SGD just a bit of a mathematical sleight of hand?
It definitely feels like one, but it operates as a vital theoretical scaffold. With a strictly non-degenerate matrix, they can invoke the duality method, leveraging Alessio Paretta's recent framework.
Okay, how does that work?
Instead of trying to directly prove convergence of the forward Fokker-Planck equation, the duality method analyzes the dual operator, which takes the form of a backward Ornstein-Uhlenbeck equation. Yeah, and by proving that the oscillation of the solutions in this dual backward equation decays over time, they can bound the moments of the forward probability measure. This establishes that for the noisy SGD variant, the distribution converges exponentially to a unique, smooth, stationary measure.
I see. But we still need to connect that back to real SGD.
Right. And they do that by using noisy SGD to construct a parameterized family of stationary measures. Once they've established that a unique, steady state exists for every positive delta, they apply Prokhorov's theorem.
Ah, so they assume the loss function exhibits superquadratic growth at infinity to ensure the family of measures is tight.
Exactly. And then Prokhorov's theorem guarantees the existence of a weakly convergent subsequence as delta approaches zero.
So they literally prove the limit exists as the artificial noise is entirely squeezed out of the system.
They do. In Theorem 1.5, they successfully prove the existence of at least one invariant probability measure for the original strictly degenerate SGD process.
That is beautiful. The steady state is mathematically guaranteed for the actual algorithm used in practice without any artificial modifications.
Yes, but there's a catch. Taking the limit as delta goes to zero proves a stationary measure exists, but it strips away our ability to calculate a constructive rate of convergence.
Right. It tells us we will eventually reach a steady state, but not how fast we get there when operating in the purely degenerate regime.
Exactly. So to solve the rate problem, the authors pivot to a completely different approach, the Bakry-Emery entropy method.
Oh, where the relative entropy acts as a Lyapunov function, right?
Right, quantifying the distance to the steady state. To guarantee that this relative entropy decays exponentially over time, the system must satisfy a weighted Poincare inequality.
Which usually involves bounding the variance of the distribution by its Dirichlet energy. But this method brings its own severe restrictions, doesn't it?
Very severe. It generally requires a quadratic loss function and a constant diffusion matrix. But more importantly, it requires Hermander's condition.
Hermander's condition? That is mathematically fascinating. In practical terms, even if your diffusion matrix is completely singular and lacks noise in millions of directions, Hermander's condition implies the deterministic drift actively rotates or pushes the system into the specific subspaces where the diffusion is active.
Exactly. The deterministic and stochastic forces cooperate. This ensures the entire state space is still fully explored, which allows the relative entropy to decay smoothly into a regular L1 density function.
But the paper goes further, right? In Theorem 4.13, they explore what happens when that cooperation breaks down entirely.
Yes, the non-Hermander edge case. It is probably the most compelling section of the paper. They partition the parameter space into two orthogonal sets of variables, a set X where the diffusion is active, and a set Y where the process is purely deterministic.
And crucially, the drift is structured so that it never couples the I variables into the X variable.
Exactly. The deterministic flow never pushes the silent parameters into the noisy subspace.
Well, if the variables never interact, the steady state can't possibly smooth out into a normal probability density function.
It doesn't. It collapses into a purely singular measure.
Oh, wow.
Yeah, the asymptotic distribution resolves into a standard Gaussian spread across the diffusing x directions, multiplied by a Dirac delta function in the non-diffusing y directions.
A point mass of infinite density, centered at 0.
Exactly. The stationary measure is basically g infinity of x times a Dirac delta at 0 for y.
The mathematical heavy lifting required to prove convergence to a singularity is just staggering to me. I mean, the system completely violates Hermander's condition. The steady state is a literal Dirac delta in certain dimensions. Standard entropy methods disintegrate here.
They totally fail, yet the authors still prove exponential convergence. They achieve this by abandoning relative entropy entirely and proving contraction in the 2-Wasserstein distance.
Measuring the optimal transport cost.
Right, the cost required to morph the current probability distribution into that singular steady state. It demonstrates that the stabilizing power of SGD is incredibly robust, even when the underlying geometry is pathological and non-cooperative.
It reinforces the resilience of the algorithm for sure, but I feel like it also exposes a pretty profound vulnerability.
How so?
Well, the precise geometry of that final parameter distribution, whether it is a smooth Gaussian or a collapsed Dirac delta, is entirely dictated by the structural shape of the degenerate noise matrix Q of x.
Absolutely. It is entirely dependent on it.
Which perfectly frames the whole analytical journey we just took. By lifting SGD out of a discrete loop and mapping it as a continuous Fokker-Planck PDE, the authors stripped away the algorithmic noise to expose the underlying fluid dynamics.
We tracked the probability mass as it was violently pulled into local minima during the deterministic drift regime.
And we saw how a single dimension of positive variance can push the system over a ridge during the diffusion regime. And finally, we saw how the duality method and 2-Wasserstein optimal transport prove that SGD ultimately finds a steady state.
Even when crippled by massive rank deficiency and non-Hermander topological failures, the PDE perspective doesn't just explain that SGD works, it maps the exact geometric constraints required for it to work.
I love that. And, I want to leave you listening with a thought regarding the future of model architecture, based heavily on that final conclusion.
Yeah, the paper really opens the door for some wild possibilities.
It does, because the paper rigorously proves that the escape times, the rate of convergence, and the exact geometry of the final steady state are entirely at the mercy of the shape of the degenerate noise matrix.
Yeah.
But in our current training paradigms, Q of x is not something we design.
No, it is merely an accidental byproduct of empirical covariance based on whatever mini-batch size we happen to select.
Exactly. So if the entire fluid dynamic flow through the loss landscape is strictly governed by this noise geometry, should we stop treating the diffusion matrix as a random accident?
That's a great question.
Right. If a single noisy dimension can guarantee an exit time, what could we achieve if we explicitly engineered custom state-dependent diffusion matrices? What if, instead of relying on the random draw of the batch, we injected mathematically optimized anisotropic noise to perfectly shape the continuous PDE flow of our parameters toward generalization?
We have the math to map the currents. The next logical step is to engineer the fluid.
Exactly. Something for you to consider the next time you initialize a massive training run.